Good morning students, this is Venugopal, Department of Physics, Aditya Institutions. Okay, today we will continue yesterday's topic as usual. Look, yesterday we studied about the latent heat as well as the specific heat. Later we did some examples based on latent heat as well as specific heat. After brief recollection, I will go to the next topic. Look, yesterday I given some formulas based on latent heat as well as specific heat. Look, I said latent heat and we are writing Q is equal to ml. If it is fusion of ice, we can write Q is equal to ml ice, where L ice is called latent heat of fusion of ice and its value is equal to 80 calorie divided by gram and 80 into 4200. Actually we have to write 4186, but roughly we are writing 4200 joule divided by kg. And then I said the second part of it is Q is equal to ml steam. This is called latent heat of vaporization. And I given it as L steam, or in the textbooks it is represented with LV. LV is equal to 540 calorie divided by gram. And then to convert it into SI system, we have to multiply with 4200. This is joule divided by kilogram. This is about the latent heat. In latent heat, it is the process in which heat is absorbed or heat is released during the change of state process under constant temperature. So, when a substance changes its state, that is from solid to liquid or liquid to vapor, such a particular state is called change of state. Look, temperature 0 degrees, here also 0 degrees centigrade. In this process, may the heat is absorbed or the heat is evolved. Even though heat is absorbed or heat is evolved, there is no change in the temperature. Such a process is called as latent heat, I said. And later we studied some important formulas based on latent heat. Later I said in this latent heat we can observe so many phenomena. The first phenomena is conversion of solid to liquid. And we know that this process is called as melting. Best example, look, the best example for it is ice into water. Second one, liquid to solid. This is called as freezing. The best example, water converted into ice. This is the first process. In the first process, you may convert, look, this is the first process. In this process, solid will be converted into liquid. Such a process is called melting. And then the best example for it, ice is converted into water. Don't forget, during this process, temperature remains constant. Look, very clearly, very specifically I am representing. Temperature remains constant. Now here, heat will be absorbed. In this process, solid is converted into liquid. Now in the second process, look, liquid is converted into solid. That one is called as the freezing. We can observe in our daily life also. In deep freezer, if you can keep a water bottle, after some time, water which is in liquid state inside the bottle will be solidified and it will be converted into ice. But here we have to remember one important point, that is the volume occupied by the water will be less when compared with the volume occupied by same amount of water when it is converted into ice. That is the reason water cannot be taken in glass bottles. If it is glass bottle, what will happen? This water will be converted into ice. That ice will occupy more volume. So it breaks the bottle. That is the reason we are using plastic bottles and made with other material than that of the glass. Okay, this is the first part, and don't forget, in this process, either during melting or freezing, temperature remains constant. Temperature remains constant. Okay, this is the first process. After completion of all this process, we will go to an important one called as, look, I taken two ice blocks like this, which are at 0 degrees centigrade. I will write like this. This is another ice block at 0 degrees centigrade. Now both the ice blocks are pressed with our hands. Surprisingly, after some time, if we can release, both the ice blocks stick together. Both the ice blocks stick together. Such a property is called regulation. Such a property is called regulation. Now, this regulation can be verified with a small experiment. Look, you take a very big ice block and it is kept on two wooden blocks like this. A small thread suspended to small mass is placed on this ice block, and when this weight pulls the ice block, say this thread in the downward direction, this thread passes through the ice block. So look, initially there will be a gap. There will be a gap. That gap will be completely filled when the thread comes to middle of this ice block. So this gap is completely filled. So this is a perfect example of regulation. This is a perfect example of regulation. Okay, once this thread come down, what will happen? The space, that is, here there will be a small gap initially. Look, the thread is moving like this. So when the thread is moving, in the path there is a gap. When the thread reaches to the middle, this gap is again solidified and the thread sticks exactly in the middle. Such a property is called regulation. That is given as an example in our NCERT textbook. In the olden days we were studying that one. Nowadays, look, you are taking some ice blocks inside a small glass. After 2 or 3 minutes, those ice blocks stick together, becoming like a single ice block. That is called regulation. That is called as regulation. Now, we will go to some of the important points of this one. Look, solid to liquid, I said, and then liquid to solid, and again liquid to vapor, then vapor to liquid. Then we will go for it, vapor to solid, before that solid to vapor also. These are the processes that we studied. Now look, solid may convert into liquid, liquid may convert into solid. Okay, now we are studying an important concept called as triple point. Now this is a little bit somewhat important. Look, in the beginning, when we are constructing a thermometer, you are taking lower fixed point and upper fixed points, and you know that lower fixed point is melting point of ice and upper fixed point is boiling point of water. Thereby you have two limits, lower fixed point and upper fixed point. Nowadays they are taking triple point of water as reference point to construct a thermometer. What is triple point of water? It is a point at which all the three states of matter will exist in equilibrium. So what are the three states? Solid, liquid and vapor states. Look, this is one state, this is the second state, this is the third state. In the first state, solid may convert into liquid or liquid may convert into solid. Second state, liquid may convert into vapor, vapor may convert into liquid. Third state, solid may convert into vapor or vapor may convert into solid. Okay, all these three states exist in equilibrium. All these three states exist in equilibrium at a particular point. Such a point is called as triple point. Look, I drawn a graph between temperature versus pressure by taking temperature on x-axis and pressure on y-axis. Here we can observe one important point. Look, at a particular point, all the three states of matter will exist in equilibrium. This is called triple point. Such a point is called triple point. Look, OA, OB and OC. This line is called as ice line. This is called as streamline. This is called as sublimation curve. Sublimation curve. Look, left side it will be solid. Left side of this ice line will be solid. Now look, these are the coordinates. This is 273.16 degrees Kelvin and this is approximately 610.2 Pascal. Maybe it is given in atmospheres also, 0.006 atmospheres. Of course, they may have different readings and different parameters of pressure. Generally in pascals it will be taken like this. Maybe in atmospheres 0.002 up to 0.006 it will take. Okay, but generally we are taking 610.2 Pascal, okay, as one of the units of pressure, as the coordinates of triple point. Look once again, triple point of water. What is triple point? The point at which all the three states of matter, the point at which all the three states of matter, first state, second state and third state will exist in equilibrium is called triple point of water, is called triple point of water. Look, OA representing the ice line, OB representing the stream line and this OC is representing the sublimation line or sublimation curve. So here this is hoarfrost line, hoarfrost line. This is called triple point of water. This O is called as the triple point of water. The coordinates of it are 273.16 degrees Kelvin and 610.2 Pascal generally. And beside, look, this left side solid form, right side it is in liquid form. So here it is in the liquid form and it is in the vapor form. Here solid form and vapor form to solid form. So all the 6 states simultaneously we can watch in the triple point. Okay, this is about briefly the triple point of water, or simply you can say triple point. And nowadays you are taking this triple point as the coordinate to construct a thermometer. Previously you are taking lower fixed point and upper fixed points. Look, lower fixed point as melting point of ice, upper fixed point as boiling point of water. But present we are taking triple point to construct thermometers. Okay, now we will go to the next part of it called transmission of heat. Yesterday I given a brief explanation of it. Heat transfer will take place in 3 different methods. Heat transfer will take place in 3 different methods. First one is called as conduction, second one is called as convection and the third one is called as the radiation. Third one is called as the radiation. These are the three methods that we are using mainly to look the transfer of heat: conduction, convection and radiation. The best example for conduction, take a metal rod like this. This metal rod consists of molecules like this, group of atoms called as molecules, like this. Now, when it is heated, when this rod is heated, heat transfer will take place. Heat transfer will take place to the first set of molecules. Now, it will be moved to second, second to third, third to fourth, fourth to fifth. Here the process is motion of molecules is equal to 0. Molecules are not moving, but transfer of heat takes place. Transfer of heat takes place. Such a process is called conduction. Such a process is called conduction. Look once again, without the transfer of or without the motion of molecules, if the transfer of heat takes place, without the moment of molecules or motion of the molecules, if the transfer of heat takes place, such a process is called conduction. Such a process is called conduction. The best example, heating of a metal rod. When a metal rod is heated, initially, look, if I can kept it like this, these molecules will get heat first. Now that heat will be transferred to, look, these molecules will get their capacity of heat. After reaching their capacity, they transfer the heat to the next set of molecules. That is the reason, if you can kept a metal rod in flame like this, look, the heat flow will take place from this end to this end. After some time only, my palm will get the sensation of heat. It means slowly the transfer of heat takes place. This is due to transfer of heat from the first to second, second to third, like this. But here the most important point that you have to remember is molecules are at rest. Molecules are at rest. This is the brief introduction about conduction. Now I will go for convection. Look, I have taken small vessel like this, which consists of water layers. First layer, second layer, third, fourth, fifth, like that. Now I heated this layer like this. Initially, the first layer will get heat. Now, this layer, after getting its heat capacity, its density decreases. As a result, this layer flows to the top. So, this is the first layer. Now, the space vacated by this layer is occupied by the second layer. After some time, second layer also gets the heat quantity and its density decreases, it moves to the top. So, first, second. Look, slowly the bottom layers are transferring towards the top position, because we know that density is inversely proportional to the temperature. As the temperature increases, the density of these layers slowly decreases and they move to the top. As a result, after some time, all the layers will get heat. Now look, in this process, there is a clear evidence that the first layer will be transferred to top. This was occupied by the second layer. Similarly, the space vacated by the second layer is occupied by the third layer. So, there will be movement of molecules. Molecules are moving. Along with molecules, heat transfer also takes place. Heat transfer also takes place. So in the second process, look, first one is conduction. Thereby I said without the movement of molecules, transfer of heat takes place. Whereas in the second case, with the movement of molecules only, heat transfer takes place. Such a process is called convection. The third one is called as radiation. You take sun. Look, this is vacuum. Thereby you have some medium. These sun rays will travel through vacuum as well as in a medium. But the heat quantity of the sun rays will be the same. That is a different story. Later we will study. But here I can say, if the transmission of heat takes place in the presence of the medium or in the absence of the medium, because in vacuum there is no medium. Look once again, if the transmission of heat takes place in the presence of the medium or in the absence of the medium, such a process is called radiation. So we have a clarity of transmission of heat. Look, once again I am revealing the points. The transfer of heat takes place in three different methods: conduction, convection, radiation. In conduction, the transfer of heat takes place without the movement of molecules. Whereas in the case of convection, the transfer of heat takes place due to the motion of the molecules. Okay? Whereas in the third case, if the transmission of heat takes place or transfer of heat takes place in the presence of the medium or in the absence of the medium, such a process is called radiation. The best example for conduction is the heating of metal rod. The best example for convection is heating of water taking in a small vessel, and sun rays. The best example for radiation. Radiation deals with electromagnetic waves. Okay, these are the three different methods that we will study under transmission of heat. Now first we will go to conduction. You know that if the transfer of heat takes place without the actual movement of the molecules, such a process is called as conduction. Now look, take a metal rod like this. Whose length is equal to L. Area of cross section is A. Heat enters through the first phase. Okay, I will take this one as XY. So XY is a metal rod. XY is a metal rod of length L, area of cross section A. Heat enters through the phase X. So at X, temperature is theta1. That heat leaves through the phase Y, whereas the temperature is theta2. It will take in T seconds. It takes T seconds to travel from the first end to the second end. So they said the amount of heat transfer is directly proportional to the area of cross section, and it is directly proportional to the temperature difference, and it is directly proportional to the time of flow of heat. Look, this is area. This is temperature difference. This is the time, and inversely proportional to its length L. The amount of heat passing through this particular solid or conductor, I can use the word conductor because it can conduct the heat. The amount of heat passing through this conductor is directly proportional to area of cross section, temperature difference, time of flow of heat, and it is inversely proportional to its length. So, I can write Q is proportional to A into theta 1 minus theta 2 into T, because all these three quantities are directly related, divided by L. To remove this proportionality, I will take a constant. So, look, Q is equal to, I will write a constant K into A into theta 1 minus theta 2 into T divided by L. What this K refers? This K is called coefficient of thermal conductivity. Thermal conductivity. Look once again, the process of conduction can be explained by taking a small metallic conductor. You know that conduction means transfer of heat without the actual moment of molecules. So, I taken a small conductor xy of length L, area of cross section A. Now, I allowed heat passes through the first end, that is x. So, the temperature at that point is theta 1, that heat will come through the second end y, whereas the temperature is theta 2. It will take t seconds. So, t represents the rate, say the rate of flow of heat. Okay. Now, the amount of heat passing through this conductor is directly proportional to the area of cross section, and it is directly proportional to the temperature difference, and it is directly proportional to the time of flow of heat, and it is inversely proportional to the length of that conductor. So, I combined all these parameters, and so that I can write Q is proportional to A into theta 1 minus theta 2 into T, because all the three are directly related, divided by L. You know that to remove this proportionality, we will take a constant here. That constant is equal to K. What K refers? This K refers coefficient of thermal conductivity. Coefficient of thermal conductivity. Now, look how we can define it, I will tell. Look, this is the formula that we are getting. Q is equal to Ka into theta 1 minus theta 2 into T divided by L. So, look, I can write K like this. K is equal to Q into L by A into theta 1 minus theta 2 into T. Now, what is the unit of Q? Heat quantity in SI system, joule, meter divided by area, meter square, temperature difference, that is in kelvins, this is second, meter will cancel. So, the unit of it is joule per meter Kelvin second. Already you know that joule per second, it is nothing but the power. Look, you know that power P is equal to work by time, joule divided by second. This is called as watt. This is called as watt. So, in place of joule per second, I can write the unit as watt also. So, watt divided by, look, meter Kelvin. This is the SI unit of thermal conductivity, and for insulators its value is equal to 0, whereas for conductors its value is equal to infinity. This is for insulators, this is for conductors. Look once again, Q is equal to Ka into theta 1 minus theta 2 into T divided by L. So, I can write K. What is K? Coefficient of, look, coefficient of thermal conductivity. Thermal conductivity. So, look how I can write it. K is equal to Q into L by A into theta 1 minus theta 2 into T. And don't forget, the value of K is equal to 0 for insulators, K is equal to infinity for conductors. Now, its unit. To calculate or to derive the unit, I have taken the units of each parameter. For heat, joule is the unit in SI system. For length, meter. For area of cross section, it is meter square. Okay, and then Look, this meter will cancel by one time. So joule divided by meter Kelvin second. So look, joule per second is nothing but the watt. Joule per second is nothing but the watt, because you know that power is equal to work by time, power is equal to work divided by time. So joule per second is the unit for power, and you know that joule per second is also called as watt. That is the reason I written in place of this joule by second as watt. Watt divided by meter and degree Kelvin. This is the unit for K, which is called as coefficient of thermal conductivity. Now look, again I am writing the formula Ka into theta 1 minus theta 2 into T by L, or Q into L by A into theta 1 minus theta 2 into T is equal to K. For example, if L is equal to 1 meter, A is equal to 1 meter square, theta 1 minus theta 2 is equal to 1 degree centigrade, and T is equal to 1 second, then I can write K is equal to Q. Don't forget, theta 1 minus theta 2 divided by L, this is called as temperature gradient. Temperature gradient, and most of the times this plays major role in our problems. So look, theta 1 minus theta 2 by L, I can take it as temperature gradient. Now here look, if we can substitute all these parameters, we can write K is equal to Q. Now I will tell how we can define the coefficient of thermal conductivity. It is nothing but the amount of heat passing through, a metallic conductor per unit time. It is the amount of heat passing through a conductor of, I will tell very easily like this, it is the amount of heat passing through a conductor of unit area of cross section having unit temperature gradient in 1 second. Look, it is nothing but the amount of heat passing through a metallic conductor having unit area of cross section, unit temperature gradient, because theta 1 minus theta 2 by L, I will take it as 1. Look, theta 1 minus theta 2 taking as 1, L is equal to 1. It is the amount of heat passing through a conductor of unit area of cross section, unit temperature gradient in 1 second. That is called as coefficient of thermal conductivity. And then I will give some of the examples. Look, this is a chair made with metal. You know that metals are very good conductors of heat. This is a chair made with wood. This is called as a wooden chair, I can say. Look, in winter season, if you can keep your hand on the metal chair, you are feeling it is very cold. If you can keep your hand on the wooden chair, of course, when compared with this one, it may not be at that low temperature. Just it looks to be so normal. But in the case of metal chair, it looks to be so cold, because you know that metals are good conductors of heat. When you are keeping your hand on this metal chair, the flow of heat takes place from our hand to the metallic chair, so that we can feel the sensation of hotness and coldness. Whereas in the case of wooden chair, you know that wood is a very good bad conductor. It will take some time for you to look the condition of this one, because bad conductors are not allowing the heat pass through them. This is one of the examples just they are giving. And you have some problems on this coefficient of thermal conductivity concept. Look once again, in the case of thermal conductivity, you are completely dependent on only one formula, that is Q is equal to K A into theta 1 minus theta 2 into T divided by L. Now look, Q is equal to Ka into theta 1 minus theta 2 into T by L. I will move this Ka and L to the other side. L divided by Ka is equal to theta 1 minus theta 2 into T divided by Q. Look once again, I written the same formula here. Later what I did? I moved this Ka by L to the other side. L by Ka is equal to theta 1 minus theta 2 divided by Q into T. Now I can write like this. L divided by Ka is equal to theta 1 minus theta 2 divided by Q divided by T. Look, when you are studying the chapter current electricity, thereby you will come across a small law called as Ohm's law. What is Ohm's law? V is equal to IR. Thereby I can write R is equal to V divided by I. This R is called as electrical resistance. V, the potential difference. I, the rate of flow of charge called as the current. Now this formula looks like to be the electrical resistance, that is R is equal to V by A. Look, this temperature difference, it will create the potential, and this Q by T is almost similar to that of, look, current I is equal to what we can write? Charge by time. So here you have Q by T, that is heat, rate of flow of heat, similar to that of current. Theta 1 minus theta 2, that is almost equal to the potential difference, thereby temperature difference. So by comparing this particular formula with R is equal to V by I can write on comparing, look, I will write a little bit clearly. Q is equal to Ka into theta 1 minus theta 2 into T by L. So in the next step, L by Ka is equal to theta 1 minus theta 2 into T divided by Q. This is equal to theta 1 minus theta 2 divided by Q divided by T. Now this is L by Ka. Now you are comparing this equation with R is equal to V divided by I. This is equation number 1. This is equation number 2. On comparing equation 1 and equation 2, simply we can write L by Ka is equal to R, which is called as the thermal resistance, Look. So to calculate the thermal resistance, we are equating this one with respect to the electrical resistance. Okay. Tomorrow we will look the concept of thermal resistance and the junction temperature concepts, which are the applications of this thermal conduction. Okay. Thank you.
Beyond boundaries, international students from 12 countries and nationally 19 states. Latent Heat, rising to new origin.